Hello. So how are you? Thank you for watching this lecture video. So let's finish this math 4545. Okay. So this is our last lecture video. Okay. So in this time, we will discuss the relationship between normal distribution and t distribution and chi-square distribution and f distribution. So in applied stats 1, we have 4 tables, right? We have 4 tables. So this table, we have a z table, right? T table, and f table, and chi-square table, right? We have the 4 tables, means we have the 4 distributions. So those 4 tables or 4 distributions are really important in stats. So what is their relationship? Why we have those distributions? Okay. So this is today's topic. So at first we say that for stats, our foundation is central limit theorem or sampling distribution. So from this population, take a sample. Okay, so from the sample, we have thus with the sample mean will follow normal distribution. With mu is the same as population's mu, right? Population's average. And suppose population's standard deviation sigma, so we have thus mu sigma over radical A. Right? So this is a sampling distribution. So this is the foundation. Also, we say so. This is we can say normal distribution is very important. So from here, for general normal, we can change to standard normal. So x bar minus mu over sigma over radical A. So we denote this as z. So this follows standard normal. So we have a z table. So so we say for estimation or for testing, for once we have the data, like we have the data. Okay, we have a sample. We have those data. So from data, we can have sample size and sample mean, but we don't know sigma. We can only have samples standard deviation. So here we say sigma we don't know. So let's say sometimes we need to replace sigma by ace. So if we replace sigma by ace, so this one will follow t distribution, right? With degree of freedom n minus 1. So this is t distribution. So t distribution from a statistical point of view, we say just replace, if we replace sigma by ace, then we have t distribution, right? Then if sigma, this sigma replaced by ace, then this z will become t. Okay. And then let's say, so what is f distribution? So remember, if distribution of ANOVA, so for ANOVA, we have if distribution or if test or ANOVA test. So here we say ANOVA test, ANOVA test, and if test. We record the same thing sometimes. So ANOVA is related to if distribution. So what is ANOVA? So we say ANOVA is like analysis of variance, right? ANOVA equal analysis of variance. So here analysis meaning separate variance into parts. So the variance, so we just check, let's say the formula for variance, just this is square equal, so suppose our data is y, so y I minus y bar square over n minus 1. So this is the variance, but we just focus on the numerator part. So we denote this as SST over n minus 1. So ANOVA means we just separate this SST into parts. So SST is just some summation yi minus y bar square. So we find we can separate this into several ways. So basically we say is this equal, we can replace y by y I hat or supposed y, then plus the summation yi minus yi hat. So yi hat is supposed data or expected value. We say expect the yi or supposed y value. So how can we find this yi hat? So it depends on our assumption, right? Depends on our assumption. So let's say we say like if, let's say so in compare, let's say in compare many groups, comparing groups, we so data like this, right? So those are y, those data like those data group 1, group 2, group 3 like this. So so those are y, those y. So what is yi? What is supposed y? What is supposed data? So here in compare groups, we assume in this direction no variance, right? So no change. We assume this. Okay. So if no change, then the supposed data should be a group. This supposed value should be group mean, right? So y I hat is group average, group mean. Okay. So we assume like in this group no difference, in that group no difference. So if there are no difference, then all those numbers should be the same. So this is our assumption. So if we assume those numbers the same, then this number should be group average, right? Okay. So in regulation, so what is yi? So in regulation, let's say data is like this. Okay, so if we assume they have this relationship like y equal a plus bx. Okay, so this thing yi hat. So suppose the yi like this. So when x equal xi. So yi hat is supposed y is on this line. Yi hat is equal just a plus bxi, right? Okay. Okay. So the NOVA is just like this, like we yi minus y bar. So this is values for original y. So we split into this part plus this part. So we call this part as SSE. So L. So yi minus yi hat is L, right? And this part, this is T, and this part, so sometimes we call this as SSG or group, or SSR means regulation. So this is just the name. Okay, so how can we determine this our assumption is true, or yi or L term is very small, like yi minus yi hat is quite close. So we use this, right? We use this f value. So f value is equal SSR or SSG over SSE. Then we just check their degree of freedom, right? So this is okay. So we call those as the F value. Then we will check F table. So F table with the degree of freedom in numerator, degree of freedom in denominator. Okay. Okay. So let's say this is F value or F table. So for two-way table, let's say for chi-square, for the chi-square test, two-way table, one-way table. So chi-square test and one-way table test or two-way table test, they are the same. So we know what a one-way table, two-way table means. So we have this formula, right? We say we use this as a chi-square value. So chi-square value is equal, oh, sorry, equal summation of observed value minus expected value square over expected. So the observed value is true data, expected value is the based on our assumption what number supposed to be here, right? So for example, we have one-way table. One-way table, let's say. So here we have like a, we have three or let's say we have four catalogs. Okay, so suppose like, okay, so numbers, we have 20 here, 30 here, 40 here, and 10 here. Okay, so this is observed value. So then expected value is if if based on our assumption what number should be here. So our assumption, suppose like A 30% here, 30% should be A, 20% should be B, like okay, 30% should be C, and 20% should be D. So this is our assumption. Okay, so based on this assumption, the data should be totally, we have 100 numbers, right? Total 100. So we say based on this assumption, we should have 30 here, and 20 here, and 30 here, 20 here, right? So we say those are true data or observed data, those are expected data. So to check our assumption is true or not true, we just need to check observed value and closed value, close or not, right? So there's a formula, observed value like 20 minus 30 square divided by 30. So here 30 minus 20 square divided by 20. So we use this. So this one, we say follow chi-square distribution. Okay? Okay. So we already know those things. Okay, so we already know in apply stats 1 or apply stats 2, we already know how to use those tables. Okay. So let's say, so what is, let's check what is chi-square distribution. What is chi-square distribution? So where we have this distribution, or why we have this chi-square test. So let's check this question. What is chi-square distribution? So we can say chi-square distribution is just so to answer the question is easy. Let's say we have this x equal c1 square plus c2 square plus zr square. Then this we define, we say this x this x, oh, sorry, this x, okay, so this x just follow chi-square distribution. We say this x follow chi-square distribution. So if we have r, so we just degree of freedom r. So what is z1, z2? So this z, z2, and zr all come from standard normal. So we can say chi-square distribution is summation for this square, this square. So certainly here z1, z2, they are independent variable. Okay. Okay. So once we know this chi-square distribution, then we can find what is the f distribution. So we can say if, we also can check if is from, we say like for this f value, these things follow the distribution. S is R over degree of freedom over S is G or S is E for degree of freedom, right? Okay, so what is SSR? We say SSR equals this. SSR equals summation for this yi minus yi hat. Okay. So let's say, so we claim those things. If those things just divide by those things just like a normal distribution. Let's say if yi follow normal, those things yi minus yi, those things just like a normal square. So normal square, the distribution is a chi-square distribution. Okay, so we can say if distribution SSE is also like SE is also like a summation for normal square, right? It is yi minus. Oh, I'm sorry. This one is we replace yi by this, yi hat minus y bar. Okay, so S is E. So almost same story. We say those things also just like a chi-square distribution. Okay, so we can say what is f distribution? F, we can say f is just a chi-square over chi-square distribution. Okay, and so here if degree of freedom R1, this R2, so we need to divide by R1 divided by R2. We just standardize, right? So we can say basically, or roughly, we can say f distribution is just the chi-square value, chi-square distribution over another chi-square distribution. Okay. So what is t distribution? T distribution, we say t distribution or t value just come from this. We say x bar minus mu over s radical a. So let's say x bar minus mu. This one follow normal distribution, or we can change this to standard normal. So this equals z over. So what is ace ace follow which distribution? So ace, let's say ace equals this formula, right? xio, let's say xi minus x bar square over a minus 1, right? Okay, so we can say that xi minus x bar. So if xi normal, then this is also normal. So this become normal square. So normal square is chi-square. So we can say this equal s equal chi-square distribution with degree of freedom r, then divided by r. Okay. So this one just like a z. So over roughly we say over chi-square distribution, or square root of chi-square distribution, and over n is just the over n. So here n is just the standardized for xi, x bar, right? So divided by radical n. So we say we can forget this. So roughly we can say that the t distribution is coming from this z then over chi-square distribution. Okay, so here I need to standardize divided by r. Okay. Okay. So we can say like all those like t chi-square and a related to standard normal, related to normal distribution, right? Okay. So the other question is, okay, other questions. For normal distribution, we find its density function. So let's say density function. So the density functions for those distribution. What are the density functions for those distribution? So this question actually is tough. Okay, like even for normal distribution, density function, we have some, we need some lots of math, right? So basically, let's check this. Like, okay, for normal, let's review this. For normal, we see normal density function graph like this. So if we send it 0, so we need to find there's a function such that there's a function is continues smoothly and goes down on both sides. So there's a function should look simply there's a function as this, like negative x squared, right? But here we need to find those constant that make this function a density function. So it means all integration should be 1. And then we just, for standard normal, we need to change a little bit in general. So this kind of function is, if not center not 0, is center is like a mu. Then this function is thus. We just simplify in a little bit. So negative. So here x minus mu square. Okay, and also can divided by some constant to make this as some constant. This is k times x minus mu square, right? So this number is 2 sigma square. Saying that the coefficient is thus, let it equal 2 pi sigma. Okay, so this is a tangent function for general normal. Okay, so x follow thus mean center mu standard deviation sigma. Okay, so let's say so find the tangent function. So for normal or for standard normal, we know the tangent function. So how about chi-squared tangent function? Okay, or how about the tangent function for t distribution or f distribution? So in apply stats 1 or stats 2, we just check tables. Like if table, the t table, we can find those numbers. So the question is where those numbers come from. So actually we need to know tangent function. Saying use those those numbers just come from those tangent function. So based on this tangent function, we can find this cutoff point such that this integration until this point is this number, right? Until that point is that number. Okay, so for tangent function for this function, so let's check what is let's check the simplest one. What is tangent function for chi-square? Of chi-square. Okay, so let's try to answer that question for simplest case. Like what is the distribution? Let's check this. What is the distribution for chi-square 1? Suppose x follows us. What is the tangent function for a? Find fx. Find the tangent function. So this is such a problem. Like we know x equal z square. So what is z? Z follows standard normal, right? So we know tangent function of tangent function for z. Then we want to find tangent function for x. So such a problem is not so hard. So we say like in general we say let's say we have let's consider this general problem. We know x landing variable x. We know then we want to find y. Suppose y equal let's say gx. Y, this landing variable y is the function of x. So we know x, then find that's the function for y. Or find distribution of y. So for such a problem should be not so hard. So we can explain, we can check those kind of problems. So let's also consider like if there's a discrete situation, such a problem is very easy. Let's say like suppose x follow this distribution, x can be -1, 0, 1, and the probability okay. So probability is like 0.2, 0.3, 0.5. So we have this distribution for this x. And now we want to find this distribution for y. So this y equal x squared. So what is the distribution for y? So such a problem is easy, right? So y, so x can be -1, 0, 1. Then x squared can be 1, 0, 1. But 1, 0, 1, these two ones we should put it together. So we say y can be only 0 and 1, right? And the probability for y taking 0 is just same as the probability for x take 0, right? So y equal 1 means x can be -1 or +1. So the probability is 0.7. So such a problem we say in discrete situation easy. So how about continuous situation? So continuous situation is let's see. Continuous situation is so suppose x, for x we have the density function. For x we have the density function f x. Then for y, so this should be uppercase. For variable x we have density function f x. So for y, so basic idea is we just replace x by y. So we say y equal gx. Then from here we say so x replaced by y. So x equal, we just denote inverse of y, right? Y. Okay, so the density function for y is just this, replace x by y. So like, okay, g -1 y. Okay. But don't forget, we need to put this, but dx over dy. Okay, sometimes we put absolute value. So why we have this? This means like, remember, let's say like in integration, let's check this. We call actually those variable transformation. Like let's say, suppose we have this integrations from 0, 1. Let's say we put like x square, let's say dx. Okay. So let's say if we set y, we just use this transformation. We set x square equal y. Then we say, so this x square become y, and so we just changing variable, right? So x from 0 to 1, then y also from 0 to 1. So then here dx, we need to change, right? We need to change. We cannot put dx. We should change dx to y. So how can we change the dx? So we say we need to use this. X equal y is half the power, right? Y half. So dx equal dx equal this derivative dy, right? So this equal this derivative with respect to y is half y -half then dy, right? So this part is just dx over dy. Okay. Okay. So now we say use this, we can find the density function for chi square 1. Let's say so for this like chi square 1 is we can find because so density function for x for z is this, right? So we just use like y equal x squared, and what is x? X follows standard normal. And for standard normal, we know density function for x. We know that if x equal this, let's see, so sigma equal 1, so this equal 2 pi square root of 2 pi sigma 2 pi sigma equal 1, so e negative 2, so x squared, right? X minus mu, mu 0, so this is density function for standard normal. Okay, so for y, so we just replace, let's say, so density function, so we just replace x to y, so radical 2 pi, so e negative 2y, right? So x squared equal y. Then we need to multiply dx over dy, right? Dx over dy. So here we need to find x equal y half. So this equal half y negative half. Okay. So this is density function for chi-square distribution with degree of freedom 1. And so in general, if so, let's say, so how about x chi-square r? So chi-square r is like this, y equal like x1 square plus x2 square plus x r square. And this x1, x2, those follow standard normal. So find this density function is difficult. So we need some math, we need lots of mathematics to solve this problem. Like maybe we can use moment generating function or many others. So from here we can say chi-square distribution or density function is not so easy, and so then F distribution density function also not so easy, and T distribution not so easy. So if we want to explain very well for those problems, we need lots of mathematics. Okay, so here instead in mathematical statistics, we call such a problem is density of, so the problem is like density of summation of some variables. So those problems are not so easy. Okay. And for, let's say, like for F distribution, so let's say for F, roughly we can say F is one chi-square distribution over another chi-square distribution, right? Just divided by R1 divided by R2. Okay. So even though we know numerate, we know this chi-square distribution for numerator and denominator, then their divisions distribution is also not so easy sometimes. So we also, those kind of problem has like, we want to find density for density function, density for we call ratio. So a ratio, just that we know, let's say, suppose z, we know this x, we know y. So what is density function for this new variable x over y? Okay. So we don't want to go to those details, but we can check a very simplistic situation. So let's say, let's check this. Like suppose like x follow exponential distribution with parameter lambda 1, y also follow exponential distribution with parameter lambda 2. So exponential distribution or exponential, saying z equal x over y. So find, let's say, find density of x, density of z. Okay. I'm sorry. Okay. So there's, let's say, exponential distribution. So is also density function. Let's say, so we have this density function, x, if x is just like that. Basically just e negative lambda 1x. Okay. Oh, put lambda 1. Yeah. So if y is thus lambda 2 is negative lambda 2y. Okay. So find the density function of for something. We find a cumulative function first. So let's find this. If the small z, cumulative function 1. What is this? This is the probability for z less than z. So here this z is not standard normal. This z is y, x or y. So this equal x over y less than z. So this equals this probability, right? X less than z times y. So here, for giving z, we can find the probability. So this probability is a function of z. So then, density function of z, if z is just a derivative. Okay, right? So we just need to find this probability. Okay. So find this probability. So here we involve two variables, x and y, and this is x from 0 to infinity, and y also from 0 to infinity. So we want to find the probability for this part, x less than z y. So let's check. Okay. So which one is equal? So let's say suppose this is equal. This is x equal cy. Then x less than less than zy should be this part. Y is big, yeah. So this part, right? So we want to find the probability for this part. So we can find. So let's say. So let's go. Okay. So let's say. So this probability. X less than zy, so equal. So we just, so here's a double integration, right? So then we check x first, x from 0 to infinity, x. Then once we determine x, so y is from this y, so from c over x to infinity, so dy, right? So dy. So there's a density function for, so here we say joint distribution. We have x and y, and they are independent. So x density functions lambda 1 is negative lambda 1x, and y is lambda 2 is negative lambda 2y. So here dy. So we just need do those double integration. Okay. So here so we integrate out for x and y, only z left. Then we regard this as a function of z, then use derivative. Okay, so let's continue. Okay, so equal. Okay, so here we regard x for dy regard as a constant. So lambda 1 is negative lambda 1 x. Okay, so this integration about y, so we say this is we integrate out is just negative lambda 2. So this is c over x. So dx. I'm sorry. I made a mistake. If this is the x here, I cannot integrate out. So I made a mistake. Let's say, so y is from infinity to this point, from this point to infinity. So for x fixed, what is y? Okay, I made a mistake. Y should equal x over z, right? Yeah, not z over x. Yeah, I made a mistake. Otherwise, I cannot integrate out. So this is x over z. So here z is constant. So we can integrate this out equals infinity. So lambda 1 is, so we take negative. So here we can take x out. So coefficient lambda 1. So here also plus lambda 2 over z. Lambda 2 over z. Okay, x dx. Okay, so this one we can integrate out. So here lambda 1 plus lambda 2 over z, this is a constant. So this integrate out is lambda 1. So here integrate out is 1 over lambda 1 plus lambda 2 over z. Okay, we can put multiply z, so we can say this is lambda 1 z plus lambda 2. Okay, so lambda 1 multiply z like lambda 1 z. Okay. Okay, so that's the function. That's the function of z. So this just equal lambda 1 z over lambda 1 z plus lambda 2. So derivative with respect to z, right? Okay. So from here we can say the density function of those other distribution like f distribution or chi-square distribution is quite complicated. Okay, so but anyway, like we know those, like, all those things. F distribution, chi-square distribution, and t distribution, those come from z distribution. Yeah. Oh, one more thing. Maybe someone will ask us, like, we say other things like why from one-way table to two tables, this is follow chi-square distribution. Equal, we say use the formula, right? There's summation here. Observed value minus expected value square over expected value. So we say this follow chi-square distribution. So why? So let's say, so let's check this. Just check one cell. So this number. So this number is, we say this observed value. Let's say like suppose like how many A's in our class. So suppose so percentage for getting A is 20% or 0.2. Okay. So how many people can get A? So suppose that totally we have n students. We have n students. So how many students can get A? So based on the percentage, 20%. So this number can be observed values, or just we can say this. We don't know. Suppose like if we have n students and the percentage of getting A is 20%. So how many students got A? So we say based on this percentage is E equal n times this P, right? This percentage, 20% multiply A. But the observed value, this can change. So this actually is follow binomial distribution. Let's say for n people, this guy, we just check n students. This guy can be A or not A, or A or not A, right? So this observed value actually follow binomial distribution. We try n times, and this guy grade can be A, percentage is P, or we have 20% chance this guy grade can be A, right? Okay, so this observed value actually follow binomial distribution. So for binomial distribution, we have this. For binomial distribution, we're close to a normal distribution, where the mean is NP and standard deviation NPQ, right? Okay, so this NP is just we say expected value, and NP's expected value. and time q. Okay, so this observed value follows this normal. Okay, so we can say, okay, so observed value minus expected value divided by thus follow standard normal. So if we put a square, so we say observed value minus expected value square over so EQ. But here we say Q will close to 1 for each cell. Okay, so we say, so here we just check all cells. So this one looks like summation for those C square, right? Okay. Okay, so this actually the chi-square table chi-square test come from, because this follow chi-square distribution, or more precisely we say those things will close to chi-square distribution, right? Okay, so this is our last topic for Math 4545. So we can stop here and thank you, and okay, so thank you for watching, and thank you for taking my class. Okay, so we can stop here.